So in this video, which will be a short 5-minute video, today we're going to be speaking about hyperconjugation. Now, hyperconjugation is something that normally in the past, especially up to A level, you would have spoken about it as induction effect, okay, pulling or pushing of electrons. But in reality, this has more to do with overlap of orbitals than electronegativity. And in fact, hyperconjugation is defined as the delocalization of electrons with the participation of bonds which are primarily sigma character. So normally, conjugation happens when you have adjacent p orbitals, okay? So if you have two p orbitals, you form a double bond. Like benzene, you have 6 p orbitals, cyclic around each other, and therefore you have delocalization, complete delocalization, which we can also then call aromatic and aromaticity. But here we have an overlap of a sigma bond and a pi bond, okay? Or a sigma bond and a p orbital, because in all fairness at this point, it's still going to be a p orbital. So what happens? When the carbon is rotating, okay, remember, this bond here can rotate, okay? At some points, the orbital overlap, okay, the sp3 of the carbon and the hydrogen, the sigma bond, can interact with the empty p orbital of the carbocation. When this interaction takes place, there can be a little bit of a sharing of electrons, okay? So the electrons will be able to minimize the charge on the carbon. And this can happen 3 times, okay, when you have a methyl group. Now, in reality, carbon-carbon bonds can also do this, though this overlap is normally more commonly found when we have these carbon-hydrogen bonds. But again, if you have something like tertiary butyl group, you still have this stabilization, okay? So if you have something like a tertiary methyl group, you will have the carbon-carbon sigma bonds overlapping with the empty p orbitals of the carbocation. So there are 2 things that you have to keep in mind here. The carbocation is planar, and it's going to have an empty p orbital, and you're going to have the overlap of the carbon-hydrogen sigma bonds with the empty p orbital of the carbocation. The electrons will be slightly shared momentarily, but this will happen constantly, all the time, which will minimize the positive charge on the carbocation, okay? And this makes the whole situation where it makes it more stable, and the more alkyl groups you will have, the more stable the carbocations will be.